Okay, so let's talk about recursion, right? So what's recursion? Anyone in class? What's the idea behind?
Recursion is a technique where a function more or less passes its return value back to itself to create some output.
Okay, no, I would say your definition is good, but if you are looking for precision, it's not quite a precise definition, but really good, very good definition. So recursion is a way of defining functions, right? And that's clear. And it's a way of defining functions in terms of themselves, right? So today we are going to study recursion. Why? Because recursion is going to be very, very important for this class. If we didn't have recursion while implementing programming language features and interpreters, the code that I would write would be unreadable, the subject would be unteachable, and you would find that recursion makes life so much easier. It makes things very natural to express. It makes things very easy to read. It makes the logic of the code clear, provided you actually know something about how to read recursion. So today's topic is how to read recursion, how to write recursion, how to express your logic recursively. Okay, that's the first topic. And then I'm going to talk about some of the issues with recursion. Obviously, if you have taken any programming class, like C programming class, you might have heard about recursion in 1300. You might have also heard that never do recursion. It's a bad thing. It causes performance issues, and it's, if you're not going to have performance, what's the point writing code, right? So in code writing, in software, there is always this tension between writing performant code and writing readable code. It would be so great if you had both, right? Both readability and performance. So we will talk about how you can get some of that, right? How you can have your cake and eat it too, using a concept called tail recursion. So it's the kind of recursion that doesn't cost you anything, provided your compiler steps in and does something nice for you called a tail call optimization. So 3 topics today: recursion, performance hit that you get from recursion, things like stack depth, things like number of recursive calls. Oh my God, this is slipping. All right. And last but not least, I'm going to talk about tail recursion, and then we'll talk about how can we write things in a tail recursive manner. Okay, which is a topic we'll revisit in this class like quite a few times. All right, this would be the first iteration of that topic. There will be a second iteration of that topic later on in the semester, where we will talk about, how tail recursion can be done in a systematic manner, how you can take any non-tail and make it tail. Okay, those are the topics for today. So let me start with recursion. The simplest function that we learn how to write recursion with is the factorial function. So why not start with the factorial function? Okay, so this is the factorial function. It's a function that takes in an integer and returns an integer. If the integer that you pass in is less than or equal to 0, including 0, I define the factorial function to be 1. So 0 factorial is 1. Okay, that's taken by convention in mathematics. What about minus 1 factorial and minus 2 factorial? Well, they tend not to make any sense in mathematics. So what you simply do is define them out to be 1, make life easier. Okay, we could argue what a factorial is and something called gamma functions if you're really interested in math. To generalize factorial, it's called the generalized factorial. But let's not go into that. All right, so let's just define it to be 1 if n less than or equal to 0. Otherwise, here comes the recursive part. It's n times factorial n minus 1. All right. So let me ask 2 really, really simple questions here. The first simple question is does this work? Do you think this code is correct and it will correctly compute factorial? Any opinions? So you always are suspicious, right? When a professor asks, does this work? Am I missing something? Is there something that I'm not seeing that's there? Will I be made to look like, a foolish person in front of the entire class? No, absolutely not. No tricks here. It works, okay? If you are thinking that this looks correct, it is correct. No problem. I'm not like trying to pull your leg here. This is fine. There are some people who might say, this is not quite fine. This is, by the way, diversion, okay? What do you think will happen if I did factorial 100? Let's see. 0. So anyone care to explain why this happened? This is, by the way, completely like orthogonal. This is not on topic. Yes, please. You're right. So integers in Scala, this type int is not arbitrary integers. It's 64-bit integers. Factorial 100 is so big that it overflows. You can't put it in 64 bits. So as a result, at some point after overflow, it became 0. And once you multiply something by 0, it's 0. Is that okay? So at some point, factorial, I guess factorial of some number overflowed so much that it overflowed and wrapped around to 0. Once it wraps around to 0, it's a 0. Is that okay? So in Scala, there is a type called big int, which is arbitrarily large integer that grows in size as you do more and more multiplication. And if you use big int, it's a Java type that comes into Scala. If you use big int, you would get the 100 factorial. I mean, if you really want to know what 100 factorial is for some reason, then you would know. But use big int. This kind of int is not going to work. So other than this little thing of, int being 64 bits and not being big enough to represent factorials, this is a proper factorial function. I will be okay with it. It will work up to, I would say, factorial 32 or something like that, or something, and then it will become nonsense as soon as it overflows. Oh, okay, dynamic memory allocation is generally not something you worry about in Scala. Under the hood, big ints are implemented in like the JVM and under the hood in a C program, in a native C program, and there you would use dynamic memory allocation. Here, you wouldn't think about it quite that way. Okay, so the question of dynamic memory allocation, like when big int grows in memory size, who is doing the malloc and free and the new, that's under the hood. We don't care, right? We don't care. In Scala, it just allows us to see a type that just grows. How it grows, how that's implemented, well, that's abstraction for us. We don't need to worry about it. Thank you. Any other questions? Okay, so now tell me give me an argument for why this kind of factorial function does not go into an infinite loop.
Because you have a base case.
You have a base case?
Go ahead.
No, go ahead. I'm repeating your argument.
I was just going to say because there's a base case, and every time that you recall the function, you're decrementing the parameter which is defining the base case.
Very good. Excellent. The answer here is that every time you are recursing on factorial, let's say 100, the next call is to factorial 99, something smaller. Then the next call is to factorial 98. So something is decreasing on every factorial call. So you're going to have a sequence of factorial calls that are approaching the base case. The base case is when the number becomes negative or 0 or negative. So there is this constant approach towards a base case. And when you hit the base case, you immediately return. There is no more recursive call. Okay? And that's the reason why this terminates. This can be made really formal. I study a field called program analysis, where we do a lot of work on how do we automatically prove that programs terminate, that programs don't loop forever. I posted about the Zune bug and some research I did around that time, right? So part of it was how do you prove program termination or show examples when you have infinite loops in programs and do that automatically, right, inside a compiler. And part of that is we study these things called ranking functions, and we derive ranking functions and we prove these things terminate. Okay? Termination proof is a very well-established field, but very difficult problem in computer science. It's related to something called the halting problem. If you take theory of computation, you would study about halting problem and why you cannot solve the halting problem in general. It's the same idea. You cannot prove that a recursion terminates inside a computer because computers are incapable of reasoning about other computer programs in this way. All right. So in this case, though, it's very, very easy. The termination argument is one line. Factorial n calls factorial n minus 1, and the base case is 0 or lesser. So there is obviously termination, but be careful. If I had written the base case n equals 0, is this considered a terminating program? So the same argument applies, right, for positive numbers. So for positive numbers, you're making progress towards your base case. Base case is 0. If your number is positive, it's decreasing at every step. You're getting to 0. But remember, int is not just positive numbers. Int is also negative numbers. So what happens with negative numbers? Yes, back there. Infinite loop, right? You're just going to keep decreasing. Well, technically, the 64-bit argument means that you won't get to an infinite loop. What will happen is you will keep decreasing after 2 to the power 64 steps, okay, or 2 to the power 63 steps. You would wrap around, go to the biggest number possible, and then keep decreasing all the way up to 0. But to me, that's non-termination because that is going to take 2 to the power 64 steps to come back to 0, okay? 2 to the power 64 is 10 to the power 30 something, more than the number of atoms in this room. So, no, we don't rely on those. So for us, it's non-terminating as far as we are concerned. Good? Because it's going to decrease forever. Now you could say, hey, you just told me factorial doesn't make sense for negative numbers, but I have to do something about it. In my notes, I talk about writing preconditions and making sure that people are only allowed to call your recursion on things that you're comfortable calculating. So you might want to write a precondition. Right? So you might want to write something like an assert. Or you don't, and this kind of an assert is called a precondition. Okay, so far? So I made a gentle start towards recursion. We talked about termination. We talked about the difficulty of proving termination. Let me talk about another recursion. So here is another recursion. So this is the second kind of recursion. This is the Fibonacci number kind of recursion. And everyone knows about Fibonacci numbers, so I'm hoping I don't have to say too much about Fibonacci numbers, okay? So what are Fibonacci numbers? Well, these are numbers where if n is less than or equal to 2, then the answer is 1. You can define it in various ways. The base case can be defined in various ways. Otherwise, what was said? It was Fibonacci n minus 1 plus Fibonacci n minus 2. So here you have not one recursive call, but you have two recursive calls, one to n minus 1, another to n minus 2. Okay? By the way, when I was interviewing for coding positions long time ago, I won't tell you how long, this was a favorite question of interviewers. They would ask you to write Fibonacci, and they would ask you to make it practical. Okay? And you would see in a second that this kind of writing Fibonacci numbers is impractical. It's going to blow up. Right? But anyways, this is the simplest and the most natural recursive formulation. Because think about it. This is how Fibonacci himself, defined his numbers, and this is how we are writing the code. How much less, how much more natural can you get here, right? The code is exactly as you would write a math definition. Great. And that's what recursion gives you. This convenience of writing code that's very close to the definition. Everyone okay with Fibonacci? Okay. What is the termination argument here? Why would this terminate? Why would every call to Fibonacci terminate? Anyone? Go ahead.
Because you go.
No, go ahead, please.
Because for any time that your value of n is less than or equal to 2, that condition is always going to be true?
Yep. So the idea is to see that every recursive call is calling back something that's smaller than itself. So if I am being called on Fibonacci 100, I am issuing calls to 99 and 98. So as long as that's decreasing, every recursive call is making some progress towards the base case. And because it's making some progress towards the base case, eventually you do hit the base case. It's not a complicated argument at this point, okay, to see that this terminates. Okay, so far? And, again, this is getting too elementary. I will speed it up, but I just wanted to start at some place where, because I didn't run a cell. In Jupyter Notebook, you always have to run a previous cell before you run the next cell, okay? Otherwise, you get into trouble. Like you have to run the cells in some sequence, and when I run Fibonacci of 10 without running the previous cell, it tells me that it can't find a Fibonacci function because obviously I didn't run the cell. Just having a cell doesn't mean you run it. Okay, lots of people posted queries on Piazza about it. Just wanted to make sure that was okay. All right, Fibonacci is good. Now, obviously, I can do something like this. But you see this star. Many of you solving the assignment would know what this star means. The star means it's still computing. Okay, and this is going to compute for a while. Do I have my computer plugged in properly? Good. Hopefully not going to crash my computer, but it's going to take a really, really long time. Fibonacci of 100. Why is that?